Hello, everyone. Let's take a look at this LeetCode problem. This problem is in the weekly context, and it's the third problem. Although it's in third problem, the acceptance rate is not very high. And once the context finished, it's only about like 20%. So it's a very comprehensive graph problem, and there are many knowledge in it. So you can practice this problem multiple times to enhance the graph theory. Okay, let's take a look at this problem. The description is a little bit like hard to understand. So if you haven't read the problem, you can take a look at this problem in LeetCode. I just talk about one example. So in this example, there are 5 nodes, like highlighted in black color. This is node 1, this is node 2, this is node 3. And you can also find the edge has a weight. Also, what is the blue color? So the blue color means like the shortest distance between this node and the end node. The end node is 5. Like in general, the end node is n. Yeah, when n is 5, end node is 5. So for example, the blue color is like 4 here. So 1 can go to 3 first, then 3 go to 5. So it's 4. So this problem asks us to find the restrict path. What's a restrict path? So the start node is 1, end node is 5. The restrict path is like the decreasing path, like for the blue color, like 4, 2, 0, it's 1 path, and 4, 1, 0, and also 4, 2, 1, 0. So there are 3 restrict paths, and we need to calculate how many restrict paths in the graph. Yes, there can be a lot, like tons of restrict paths. Okay, so how to solve this problem? Of course, we need to calculate the blue number first. So it's a very typical graph problem, like shortest paths. Okay, so first we have this graph, and I use this data structure to represent the graph. And the distances variable is like holding the blue numbers. And I also have a data structure called closest nodes. Basically, the closest node is a node that's sorted by this blue color. So after BFS, the closest nodes will be like 5, 3, in descending order. 4, 1, 2, 3, 5. Yeah. Okay, let's take a look at the implementation of the BFS. So it's a very classic implementation. We have a priority queue, and we have a visited variable. And first, we push n0 to our priority queue, since the BFS starts from 5. Okay, as long as queue is not empty, I get the top node and pop the top node. If it's already visited, I just ignore it, continue. Otherwise, I update my distances and set visited to true, and also push my current node to closest nodes. Then I just visit every neighbor and push the neighbor into the queue as long as this neighbor has not been visited yet. So after BFS, the closest nodes will become like 5, 3, 2, 1, 4. Okay. Now we initialize a DP data structure, and for 1 we set it to 1, since 1 is our starting node. Finally, I just return DPN. The meaning of DP is how like the number of restricted paths from my starting node to current node. For example, for DP3, it will be 1, since from 1 to 3, there is only 1 restricted path. Okay, so our answer is DPN. Let's see how to get DPN. So first, DP1 is 1. For others, they're all 0. And we will iterate from the end. So first, we get node 4, we process node 4. And we will visit all the neighbors, and we can contribute the value to its neighbors. But since the value is 0 for node 4, so it's a no op. Although 4 is not our selecting node, but it's a no op. Okay, next node is 1. So I can contribute 1 to 2 and 3. Next node is 2. So I can contribute 1 to this node and this node. Next node is 3. I can contribute 2 to node 5. At last node is 5. Then we just finish and return dp5, which is 3. Okay. So that's the solution to this problem. It's a very good problem, I think, and like you can practice a lot of algorithms in graph, and also you can like use the DFS for this problem. That's it. Thanks.